Next up, we have Moritz Maier, who's the CEO and co-founder of Synera, who'll be discussing how they're implementing these ideas and how they're seeing this adopted in industry now. Okay, to you, Moritz.
Yeah, thanks, John, and thank you very much also, Blake, for this amazing keynote. I realized our roots in Grasshopper, it's perfect, right? We realized, okay, nice tool, visual scripting, but unfortunately no geometry possible that we engineers love, like Parasolid kernel, and that's the origin. So a long story that we've been taking, but today I want to take the chance to talk about a very exciting, I would say, a new thing, which has been around since roughly now 2 years. It's about AI agents and how they can actually be added to engineering tasks. And I think it all started with kind of a question that we ask ourselves in terms of why actually should we do this? And we ask our customers a little bit, what do you think on an individual basis? So one engineer, what is the efficiency that an engineer has today? So how much time actually does it spend on a CAD system drawing, or how much time is an engineer sitting in the coffee kitchen? And kind of we got this number of roughly 50% of value at a time. So this actually means that half of the time engineers are sitting in meetings, waiting for somebody to send over information and stuff. So this is kind of like an inefficiency, but that's really good in with classical automation, could be solved on an individual level. But if you look into a more broader scale, let's say a whole car or an airplane, like systems, things get more complicated. And usually we then talk about, let's say, the V model or product development processes, where you need to connect lots of different tools. We need to talk to over different departments. We have alignment meetings, synchronization points, and then things become really inefficient. So you just wait for somebody who is on vacation, or everybody needs to wait for the simulation department to send over the latest results in order to then change the design. So then it's human communication actually which slows down. And if you think about an R&D organization, how these are typically set up today, it's also something which is kind of inefficient, because you have lots of steering managers on top, and the engineers are only a fraction of the people. And unfortunately, these kind of interactions, so human to human interaction or alignment, that's super hard to get automated by the classical processes like rule-based automation or RPA. So we need something better here. And I'm sure who of you might have seen the movie Iron Man. This was one of the sparking moments when we founded the company Synera. Tony Stark and Jarvis, this wonderful AI system where he can interact as an engineer like a co-pilot and just get things done, develop. But this is the goal. And then we thought, well, what about we could actually develop such a system for engineers? And it all started with the foundational basis of process automation. And this is rule-based, it's classical, if this then that, or adding geometry, generative design, for example. But at some point we realized, well, this is not enough. We need to have some kind of intelligence in the room. And it was last year, actually, 2024, that for the first time, a technology came out, which is called agents, that you might be familiar to, that actually closes the gap between the AI world, machine learning world, and the engineering ground truth. And the cool thing about an agent is basically it consists of 3 different ingredients. There is the large language model or language model in general, could be ChatGPT or Gemini or these kind of models, and you can give it an introduction. So for example, oh, please act as a mold expert. Then of course, these agents have some kind of memory functions and can also get the company knowledge in here. But still, this is only the LLM world, the AI world. So there's no possibility to really run a mold flow simulation. But the cool thing about the agents is that they have access to rule-based knowledge. So they can call workflows or functions. And in these functions, actually, we can build logical workflows where, for example, an agent then can connect to a mold flow simulation. So this is cool. One agent can do pretty cool stuff. But let's take it one step further, because engineering is even more complex, and usually we're working in teams. So what we thought, well, what about we could not only add one single agent to the game, we could add multi-agents. And so think about having a kind of a structure where multiple agents interact with each other, where you have maybe a supervisor agent who steers the whole team, and you have special design agents who can do CAD or simulation or costing maybe. This would really become a smart system of engineers who then can fully autonomously do engineering tasks. So yeah, great idea. So let's walk through how this is possible. And I also want to show you an example. So I would like to boil it down into 4 steps that are necessary to build such systems. And it all starts with the very foundational principles of the data, the automations, and the tool connectivity. So as we have built this visual programming language, this is an amazing vehicle to really have a white box process automation where you can really see what's happening in the engineering field. And of course, we want to use all of the great tools that are out there. I've already seen the meshless simulations here from Intact or Ansys simulation, for example, Altair, you name it. All of these tools need to be connected. And then once you have automated them, you can actually publish those workflows and give it then either to humans or to agents. So for those of you who are not familiar to our programming language, I want to give you a very short Hello World example. That's Synera. On the right side, we have the visual interface where we see the 3D geometry. On the left side, that's the canvas where we can do the visual programming. And I want to start with some very basic blocks here, or nodes as we call them, just 2 numbers. We multiply them, and we've created a little calculator in here. So this is the basic idea. As Blake has shown, these little wires and stuff here, we can change them. The outputs get updated, and so we can calculate algorithms basically. And of course, our data is connected in any kind of data source. So whether it's CATIA or whether it's NTOP or whether it's a PLM database or an Excelis, we need to access these kind of data points and bring it into the system. And once they're there, we can kind of process them. So for example, multiply them. And we have a full Parasolid CAD kernel under the hood. So you can do geometry generation or manipulation. In this case, let's do a hello world here, grab a sphere. You created the sphere on the right side. You also see the geometry now. And if you connect, for example, now the results of the multiplication to the radius of the sphere, you have a nice parametric CAD model. So this is quite straightforward. And usually at that point, if you want to, for example, know what is the FE simulations, the maximum stresses of such a geometry, you would need to export this geometry and import it into next meshing software, for example. So if you wire those things up, you can automate them quite simple. So you can run through your processes, either mesh it with the internal capacities, or if you're then looking for your more interesting stuff, maybe go for hypermesh or something, which is your straightforward simulation software tool or a meshing tool. So in here, you just connect to the software, plug it in, and then Altair does the job. Let me maybe move this a little bit forward here. So you now see the mesh from Altair. It looks a bit nicer, and you're ready to go. So let's assume you have wired all of these workflows up, and you want to share this now with somebody. The thing what you need to do is you need to define what is input and what is output of these functions. We can do this quite simple by clicking on these numbers and then maybe say, okay, the area is the output that we are interested in, inputs these 2 numbers. And then if I publish this workflow, actually, what I get in the website later is kind of like an user interface, which is super easy to access by a human. So in this case, you just get a web interface where you get the same inputs and the same outputs. In this case, just the 2 numbers here. You can manipulate them. If you click on run, the processes calculate and you get the output. So this is pretty handsome in order to share your automations. And I think this could be very much known from human automation. So imagine you have calculated some costs and you give this workflow to your sales department, so then they can calculate the costs without actually needing to go down into the nitty-gritty stuffs. But this is also super interesting now, once we have these automations, to get these workflows as engineering tools in our very 4th step to agents. And we can do this basically in the same way. So we've created a user interface which kind of enables you to create agents, super agents, and single agents. You can wire them up, and you can then also connect the large language models, prompt engineering, everything in the same UI, and really build multi-agent systems. And I want to give you an example of a very interesting RFQ use case or costing use case, which kind of makes this more tangible for you, that you can think about what's happening here really. So imagine you want to calculate a cost for such an assembly. Usually what is the case is that in your team, you have a costing manager. Then you have maybe 4 or 5 individuals who are, for example, experts in accessing your PLM database, looking into what features of goods do we have off the shelf. Maybe somebody who's really good in how should we assemble these tools, a purchasing analyst who then can define, is it single vendor, multi-vendor strategy? Maybe you have a costing expert who can calculate the costs And of course, you need to have the CAD expert who can measure wall thickness and stuff like this. So let's imagine you want to convert this organic RAM or this team into kind of like a multi-agent system. You can do this by simply creating a graph representation of your system with these nice wires. And then once you are done, what you actually get is something close to Jarvis. So it's something where you can interact with as a human and really let this whole team of agents do their job. So let's ask the first question. How can you help me? And you can see on the right side here, the so-called traces, what happens now in the background. So in this case, the manager answers, he knows its team and says, well, I can do technical analysis, I can do geometry analysis, I have access to our supply chain, I can do cost analysis and things like that. I need to have the requirements and then the system can start. Now we can go into the system with a super high level prompt. So for example, here you can see we need a system of a flow rate, 300 cubic meters per hour, pressure drop, 1.3 bar, mass around 250 gram, and it should be produced 7,000 parts per annum in our standard delivery option. And when I first saw this kind of thing, which happens down here on the right side, like these agents talking to each other, calling the real software tools, calculating the prices, downloading things from the PLM world, analyzing the geometry, this is really fascinating to watch on the one hand, but it's also a disruptive way of having an engineering team working, because here in the background is actually the real tools, remote control, the real calculations done, and everything wrapped up under a autonomous acting multi-agent system. And then after a couple of seconds, actually, we get the full result of the system in here. I guess it takes roughly 4 minutes here. And you see on the right side, yeah, we found the system. This is the outer diameter. We have validated the pressure drop. We would select snap-fit designs. Lead time is 34 days. It costs €1 per part. And yeah, it's the standard delivery option. And we also calculated the risk. And of course, you get the real results, right? You get, for example, the cost breakdown structures, or you can download the CAD files. So it's really something where you can work with. And I think this is an amazing future that we're looking for, having this combination of AI agents working with engineering tools together to get the real physically correct results in their existing software tools, but more on a very intelligent and autonomous way. So I think amazing times ahead, and it's definitely something that I'm looking forward also for the discussion later, how mature this is already or not. And the question is just, are we ready for this change when AI agents are heading towards our engineering domain?
Super exciting. Thank you for that, Moritz. I guess what we see the questions of the data. So like how much data the people have. We may be ready for AI agents in engineering, but is the data ready for it? Is the big question that I often get posed with.
Absolutely, absolutely. I had like one answer, which I can throw in quite quickly. No, we are not. But we don't have to actually. So you don't need to have all the data prepared across all of your product development process and all the tools. You're looking for impact actually. So there might be one domain where the data is ready. That's the way you get started, and there you can add value. So it don't need to be perfect at the beginning.
Yeah, you need to build the pyramid upon the data.
Exactly.
Yes. Awesome. Thanks so much.